Hi students, in the last video we have studied how to simplify a Boolean function in SOP form using Karnaugh map. In this video we will study how to minimize a Boolean function in POS form using Karnaugh map. You know what is a POS form? Product of sum form or product of max terms. Okay, suppose you have a variable x. X can have two values, 0 or 1. In the case of a min term, when x is equal to 0, x is represented as primed, that is x bar, and x is equal to 1 unprimed, that is x. But in the case of max term, if the value of x is equal to 0, it is unprimed, and value of x is equal to 1, it is primed. Okay. Min term means AND of literals, but max term means it is OR of the literals. Okay, so that is the difference between min term and max term. A Boolean function can be expressed as sum of product expression or product of sum expression, that is sum of min term or product of max term. Okay, so in the case of a sum of min term, we take values of min term whose output is equal to 1. That means suppose we have given a truth table. From the truth table we take the output is equal to 1, the min term whose output is equal to 1. Then take the OR of the min terms. It is the Boolean function. Okay, in the case of max terms, we take the max terms which have value is equal to 0 in the function. Okay, then AND of these values. Okay, suppose we have given a function ABC is equal to pi m of 0, 1, 2, 3, 4, 7. Okay, simplify this product of some expression. Okay, so first we have to draw the K-map. So the K-map have 8 squares. So here it is the variable A, then BC. Okay, so BC can have value 0, 0, 0, 1, 1, 1, 1, 0, and it can have value 0 or 1. So we can mark the terms. Here it is 0, max term 0, max term 1, max term 3, 2, 4, 5, 7 and 6. There is no difference between the K-mapping, K-map for the sum of product expression. Same way we draw the K-map. Okay, then mark the entries. These entries 0, 1, 2, 3, 4, 7 entries are 0 because it is a product of some expression. Okay, so mark 0 for the entries 0, 1, 2, 3, 4 and 7. Next we can group. So here these 4 zeros are adjacent, so we can group them. Then here these two are adjacent, so here it is grouped as a pair, here also grouped as a pair. Next we can write the expression for this quad. That means here B and C variables are cancelled, only A. Okay, so in the case of a max term, when A is equal to 0, it is represented as A itself, unprimed. And next expression for this pair, here A is cancelled, we have only BC. B is equal to 1, C is equal to 1, that means B bar plus C bar. Next for this pair, here also A cancelled, we have only BC. B is equal to 0 means B plus C is equal to 0 means C. So we get the simplified Boolean expression as f is equal to A into b bar plus c bar into b plus c. This is a simplified Boolean expression. Okay, that means here we write 0 for the maximum entries and then grouping. Grouping is similar to the SOP form. Okay, no change. Next we can implement this simplified Boolean expression using basic gates and also universal gates. So how can we implement this simplified Boolean expression using basic gates? Okay, so first term is A as such. Then second term is b bar plus c bar. That means we have the input b. It is NOT gate. It is given to the NOT gate. We get the outputs b bar. Then also we have c, input c. It is given to a NOT gate. We get the output c bar. Then over the b bar input and c bar input. That means we get b bar plus c bar. So we have the first term A, then b bar plus c bar, then this b and this c put together, we get b plus c. So we have three terms A, b bar plus c bar, b, c. It is given to a AND gate, 3 input AND gate. So we get the output as A into b bar plus c bar into b plus c. Okay. Next we can implement this using universal gate. So here it is a POS expression. So here we use the NOR logic. So to implement this using NOR logic, we write it as A into b plus c bar into b plus c double bar. Okay. So we have to remove this AND operation. So we apply De Morgan's law. So that is a bar plus b bar plus c bar whole bar plus b plus c whole bar whole bar. Okay. So here we have a input. It is given to a NOR gate. By connecting the input together, we get the output as a bar. Similarly, for the b input as b, we get here b bar, and also for c, here we get c bar. Then take this b bar and c bar input connected to another, given to another NOR gate. So the output is b bar plus c bar whole bar. Then take b input and c input, and it is given to another NOR gate. We get the output as b plus c whole bar. Okay. Next we take the input a bar, b bar plus c bar whole bar, b plus c whole bar, and it is given to another NOR gate. Okay. So here the output is a bar plus b bar plus c bar whole bar plus b plus c whole bar whole bar. Okay, we implement it using NOR logic. Clear? Consider another example. F of ABCD is equal to sigma m 0, 1, 2, 5, 8, 9, 10, 9, 10 in POS form and SOP form. Okay, so first we simplify the expression in SOP form. So this is a 4 variable Boolean function. So we have to draw a 4 variable K-map. So this is the 4 variable K-map. Here we have AB, and here it is CD. So 0, 0, 0, 1, 1, 1, 1, 0. Here also 0, 0, 0, 1, 1, 1, 1, 0. Okay. So the minterms, we can write the decimal value of the minterm in each square. That is 0, 1, 2, 3, 4, 5, 6, 7, then 8, 9, 10, 11, 12, 13, 14, 15. Okay, so this Boolean function is SOP form, so we can mark these minterms as 1 in this K-map. Okay, so here 0 is equal to 1, then 1, 2, 5, 8, 9, 10. Okay, next we can do the grouping. So here we can group this 2 pairs and this 2 pairs form a quad. Then we can again form a quad by the corner elements, by grouping the corner elements like this. Next we can group these 2 pairs. Okay, so there are 1, 2, 3 groups. So for the Boolean expression for this corner element is, so here it is 0, 0, 1, 0, A cancelled, then B bar, then for these two 0, 0, 1, 0, C cancelled, D bar. Okay, then for this quad 1, 0, 0, 0, that means B bar, then here 0, 0, 0, 1, that is C bar, D is cancelled, C bar. Then for this pair 0, 0, 0, 1, B cancelled, that is A bar, here it is C bar, D. Okay, so our Boolean simplified Boolean function becomes F is equal to B bar C bar plus B bar D bar plus A bar C bar D. This is the simplified SOP form. Okay, next we can implement this simplified Boolean expression using both basic gates and NAND gates. First we implement using basic gates. So here B input, that is complemented, so we get B bar. Next C input complemented, we get C bar. Then next both B bar and C bar ANDed together to form B bar C bar. Next B bar input is ANDed with D bar. Okay, so this is the D input, these two are ANDed together, we get B bar D bar. Then next we have the A input, that is complemented, we get A bar. Then we have C here, this C is taken, then D, here D, then this D is taken, then given to a AND gate. So here we have A bar C bar D. Next we OR these terms. Okay, so here we have the output is equal to B bar C bar plus B bar D bar plus A bar C bar D. Okay, so this is the implementation of this expression using basic gates. Okay, next we can implement this simplified Boolean function using universal gates. So here we implement this using NAND logic. So here we write this expression as B bar C bar plus B bar D bar plus A bar C bar D double bar, because we have to remove the OR operation. So x double bar is equal to x itself. Okay, so we apply De Morgan's law. So B bar C bar whole bar dot B bar D bar whole bar dot A bar C bar D whole bar. Now we can implement this expression using NAND logic. Okay, first we have a B input that is given to a NAND gate. Here we get B bar. Similarly, C is given to here we get C bar, because here the inputs are connected together. So these two are NANDed together. We get B bar C bar whole bar. Next is this B bar is taken. Okay, then here we have D. Okay, so here we have the D bar. So B bar and D bar NANDed together, we get B bar D bar whole bar. Okay, next we have A input. It is given to an AND gate. Here we get A bar. Then this C is taken from here. So here we have C bar. Then D input from here. This to given to another NAND gate. So here we get A bar C bar D. Next, these three inputs are again given to another NAND gate. Okay, so here we get B bar C bar whole bar dot B bar D bar whole bar dot A bar C bar D whole bar. Okay, so this is the implementation of this expression using universal gate, right? Next we have to find the simplified POS expression for this given expression. Okay, so how can we write the POS expression? So POS expression, here it is pi m of f is equal to pi m of complement of this one, that is 3, 4, 6, 7, 11, 12, 13, 14, 15. Okay, that means here it is, we perform the conversion between the canonical forms. We have one canonical form that is in SOP form, convert this into another canonical form, that is the POS form. So what we have done is, the terms that is not in the SOP form is written in the POS form. Okay, easy way to find out the canonical form, another canonical form, right? So this is the Boolean function in POS form. So we have to simplify this one. So for this we draw the K-map, the 4 variable K-map. So here it is. A, B, C, D, 0, 0, 0, 1, 1, 1, 1, 0. Here it is 0, 0, 0, 1, 1, 1, 1, 0. Okay, so we can write the decimal equivalent 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? Then mark these max terms. Okay, mark these max terms as zeros. So entry 3, 0, 4, 0, 6, 7, 11, 12, 13, 14, 15. Okay, next we have to perform grouping. So here we group these 4 zeros because they are adjacent to each other. Then next we can group this 2 and this 2, form a quad. Next we can group these 4. Okay, so the Boolean expression for this quad is, here CD cancelled, that is only A and B. It is A is equal to 1, B is equal to 1, so it is primed form A bar plus B bar. Okay, so here AB cancelled, only CD, that is C bar plus D bar, because C is equal to 1, D is equal to 1, right? Then next one is this quad. So here it is A cancelled, then B is equal to 1, that is B bar, plus 0 0 1 0, that is C is cancelled, only D is equal to 0, that means D. So the simplified expression is F is equal to C bar plus D bar into B bar plus D into A bar plus B bar. Okay, so in the case of Boolean function that is in POS form also, we draw the K-map and perform the grouping. Only thing to remember is that we mark zeros in the squares. In the case of minterms, we mark 1, here it is zeros, and grouping is same as that of in the case of minterms. We can pair them, quad them, and also octet. Clear? Then another thing is, in the case of max term, if this value is equal to 1, when variable value is equal to 1, it is in primed form, and variable value is equal to 0, it is in unprimed form, and we over the literals. These things we have to remember. Clear? Next we have to implement this Boolean expression using basic gates and universal gates. So first we implement this Boolean function, simplified Boolean function using basic gates. Okay, so here we have C, D and B and A inputs are complemented. So first C is complemented to form C bar, then D input complemented, we get D bar, then these two outputs given to an OR gate form C bar plus D bar. Then we have the D input here, then B given to a inverter, we get B bar, then B bar and D OR together to form B bar plus D. Next, again take this B bar, then A input is complemented, so here we have A bar, then these two inputs are given to a OR gate, that is A bar plus B bar. Okay, then these three outputs are given as input of a AND gate. So we get the output as C bar plus D bar into B bar plus D into A bar plus B bar. Okay, so this is the implementation of this expression using basic gates, right? Next we have to implement this expression using universal gates. Okay, so here we implement using NOR gate. So to implement using NOR gate, we have to remove this AND operation. So we write it as C bar plus D bar into B bar plus D into A bar plus B bar double bar, right? Next we apply De Morgan's theorem. So C bar plus D bar whole bar plus B bar plus D whole bar plus A bar plus B bar whole bar whole bar. Next we have to implement this simplified POS expression using universal gate, that is NOR logic. So here first the input C is given to a NOR gate, we get C bar. Then D input given to a NOR logic, we get D bar. Then these two outputs are given to another NOR gate. So here it is C bar plus D bar whole bar. Okay. Next we take this D input and B is given to a NOR gate. So here we have B bar. So these two are given to another NOR gate. So B bar plus D whole bar. Next we take this B bar and A is given to a NOR logic. So here it is A bar. Then these two inputs are given to a NOR gate, that is A bar plus B bar whole bar. Okay. Next these three outputs are given to another NOR gate. Okay. So here we have C bar plus D bar whole bar plus B bar plus D whole bar plus A bar plus B bar whole bar whole bar. Okay. So this is the implementation using NOR logic. So in this implementation we have 1, 2, 3, 4, 5, 6, 7, 8 NOR gates. 8 gates. So in the NAND gate implementation of the SOP expression 1, 2, 3, 4, 5, 6, 7, 8 gates. So both implementation have 8 gates. But in some cases SOP or POS expression may be implemented using minimal logic. So to find out the real minimal logic, we have to count the number of inputs. So in this SOP expression, here A, B, C, D inputs are inverted. So 4 inputs for the complementation. Then here 1 NAND, 1 NAND, 1 NAND. 2 input, 2 input, 3 input. So 2 plus 2, 4 plus 3, 7 input. Okay. Then finally a NAND gate. This is the one input, this is another input, this is third input, 3 inputs. So there are 14 inputs for this NAND implementation. But in the case of NOR implementation, here A, B, C, D are inverted. So 4 inputs for the complementation operation. Then one NOR gate, another NOR gate, 3 NOR gate. 3 NOR gates have 2 inputs each. Okay, so there are 6 inputs. Then for the last NOR gate 1, 2, 3 inputs. So here there are only 13 inputs. Okay, so actually this NOR gate implementation is the actual real minimum expression. Okay, considering the number of inputs, but both uses the same number of gates. Clear? So this is how POS expression is minimized using K-map, and also the implementation of the minimized SOP and POS expression using basic gates and the NAND gates. Okay, thank you.